Implicit differentiation. So far in our discussion on derivatives, we've been taking derivatives of functions that were defined explicitly. And all that means is they look like y equals some function of x. So I have one copy of y equals some function of only the variable x. And to take its derivative, we use notation like y prime, or which is the same as the derivative with respect to x of y, or dy dx. So here's an example of an explicitly defined function. So y equals 3x squared minus 2x plus 1. And here we're being asked to find y prime. So here what we would do is we would jump straight to y prime equals, the power rule gives us 6x minus 2. So what we never did was look at taking the derivative with respect to x of both sides of the equal sign. Because on the left side, we knew that we would end up with y prime, or the derivative of y with respect to x. But ultimately what we were doing is taking the derivative with respect to x of both sides. So d dx of y equals d dx of the function 3x squared minus 2x plus 1. Well, the right side by the power rule is 6x minus 2. And on the left side, because of this string of equalities here, the derivative with respect to x of y is dy dx. So dy dx equals 6x minus 2. So you might be thinking, we've done this before. And it's true, but we never thought about it as taking the derivative of both sides of the equal sign with respect to x. And now that's how we're going to have to think about taking derivatives when we try to take the derivative of a function that is defined implicitly instead of explicitly. So let's look at an example of that. Alright, so here we have an example of an implicitly defined function. So given y squared equals 1 minus x squared, find dy dx. Now before we get into the process of finding the derivative of an implicitly defined function, let's take a look at what's really happening. So why isn't this explicitly defined? Well, the problem is that I have y squared here. So if I wanted to try to write this as just y equals, if I took the square root of both sides, I would get y equals plus or minus the square root of 1 minus x squared. And that should make sense. So here, an implicitly defined function, even though it has the word function, so I know it's confusing, is not actually a function, because this here is the graph, which I hope maybe you recognize, because I could rewrite this as x squared plus y squared equals 1, which is the equation of a circle with radius 1 centered at the origin. So here I have 1 and negative 1, 1 and negative 1. And so here, when I attempt to write this explicitly, two different functions come out, and each of those functions represents the top half and the bottom half of this circle, because this is not a function. It does not pass the vertical line test. I would cross 2 points at many different values of x. So that's one reason why I cannot write this as an explicitly defined function, and I need another strategy for finding the derivative, rather than just attempting to solve for y and make it an explicitly defined function. So let's go ahead and erase that. So here's what we're going to do. We're going to take the derivative with respect to x of both sides. So I'm going to take d dx of y squared and d dx of 1 minus x squared. Okay, so the right side. Pretty straightforward. Everything is in terms of x. So the derivative of a constant is 0. The derivative of negative x squared is negative 2x by the power rule. So the right side is something that we should be familiar with and comfortable with. The left side is a little bit different. So I don't just have d dx of y, which is dy dx. I have the derivative with respect to x of y squared. What I have here is really a composition of functions, so I have to apply the chain rule. But it's not so obvious why. So off to the side here, we'll explain why, and then we'll go back to this example. So let's go ahead and think about d dx of y squared as d dx of f of x as a quantity squared. Because let's remember, y is some function of x. Well, now this looks just like a composition of functions. I have f of x inside of x squared. So what I would do is bring the 2 to the front, leave the inside the same. So 2 times f of x. and then multiply by the derivative of the inside, which would be f prime of x. So now replacing my f of x with y, because we made that substitution earlier, y equals f of x, I can go right back to saying f of x equals y, and f prime of x, another way to write f prime of x is dy dx. So I have that the derivative with respect to x of y squared equals 2y dy dx. Now we don't have to go through this process every time, and we'll take a look at why. Because if you remember that this is really a chain rule here, then what I can do is take the derivative as though this were an x, so I can bring the power to the front, leave the inside the same, and then multiply by the derivative of the inside. So if I bring the 2 to the front, leave the inside the same, it's just y, multiply by the derivative of the inside, so the derivative of y is dy dx, then I get the same result as though I were truly letting y equal some f of x. And that's the strategy we're going to employ from now on, is we're going to treat y as a function of x, and when we see it, we have to remember to really apply the chain rule, which is where this dy dx is coming from. And we need it to come out because that's what we're trying to find, dy dx. So I will go ahead and erase this right side. And now I'm solving for dy dx, so I can divide both sides here by 2y. And I will only be left with the dy dx on the left, which is great, that's what I'm solving for. And on the right, the 2's will cancel, and I'll have negative x divided by y as my derivative of the y with respect to x. Now here's something new as well. We have a derivative as a function of two variables in terms of x and y. And let's think about why this might happen. So here is the original equation. It was the equation of a circle. And let's say I want to find the derivative at only an x value. So let's pick an x value of a generic a. Well, how do I know where to go? Because this isn't a function, because it passes the vertical, or doesn't pass the vertical line test. So would I be trying to find the tangent line up here, this tangent line, or would I be trying to find the tangent line down here? Well, that means we need the y value. We need the entire coordinate. So we would need a, b, or a negative b. So we would need the coordinate point to be able to plug two different values in to find the tangent line that we're specifically looking for, because it may not be unique to a specific x value. It may there may be more than one tangent line for a specific x value, because these are no longer functions. Even though I know it sounds weird because it's called an implicitly defined function, this is a perfect example of it not being one because it is a circle. So here the derivative dy dx is negative x divided by y. And we'll keep going through a few more examples. Alright, so more examples. Find dy dx given y to the fourth minus y equals x cubed plus x. So first step, take the derivative with respect to x of both sides. So d dx of y to the fourth minus y equals d dx of x cubed plus x. And remember, this is an action. It's telling us to do something. So take the derivative with respect to x. Now on this left side, the variables don't match. So this is a case where we have to apply the chain rule. So I would bring the power to the front. So I'd end up with 4y cubed. And then I'd have to multiply by the derivative of the inside. The derivative of y is dy dx. And now minus, here, the derivative of y would be just 1. So again, we're kind of thinking about this as though it were an x. So the derivative of just x would be 1, but then I have to use the chain rule, so the derivative of y would be 1 times dy dx. So it's really minus dy dx equals, and the right side is straightforward. The power rule tells me 3x squared plus 1. Well, now I have these two copies of dy dx, and I want to solve for dy dx, so I'm going to factor out a dy dx from each of these. So I'll have dy dx times the quantity 4y cubed minus 1 equals 3x squared plus 1. And then finally, to get dy dx by itself, I divide both sides by 4y cubed minus 1. So I'd end up with the derivative equals 3x squared plus 1 divided by 4y cubed minus 1. And that's my derivative. Let's go ahead and do another. This next example is a little different than the others. We still want to find dy dx given this implicitly defined function y to the fourth plus x times y equals x cubed minus x plus 2. Strategy is always the same. Take the derivative with respect to x of both sides. So d dx of y to the fourth plus x times y equals the derivative with respect to x of x cubed minus x plus 2. Now on the left side, again, we apply the chain rule. So bring the 4 to the front, leave the inside the same, and reduce the power by 1. So we'll have 4y cubed, and then we have to remember multiplying by the derivative of the inside, so dy dx. Now here's the tricky part, and so many students will forget to do this. Here, although it's not obvious, or maybe as obvious as it could be, this is a product rule. I have a function of x, just x, times a function of x, because y is really some f of x. So this is a product rule here. So what I would have to do is plus the first function x times the derivative of the second, and the derivative of y is dy dx, plus the second function y multiplied by the derivative of the first, and the derivative of y, or x, I'm sorry, is just 1. So we've completed the left side. The right side is the easier side this time. Just the power rule, we have 3x squared minus 1. Alright, so now I have something a little different than last time. I have the terms with dy dx on one side, but I have this extra plus y here. So what I want to do is move it to the other side. So we take the derivative with respect to x of both sides. And then I gather like terms, all the terms with dy dx on one side, all the terms without dy dx on the other. So what I'll have here is 4y cubed dy dx plus x dy dx equals 3x squared minus 1 minus y. So I'm subtracting y from both sides. And now I can pull a dy dx out of both terms. So I'll have left 4y cubed plus x equals 3x squared minus 1 minus y. And then the last step is to divide both sides by 4y cubed plus x. So finally, these will cancel, and I'll get dy dx equals this right-hand side, 3x squared minus 1 minus y, divided by 4y cubed plus x. As you can see, these implicit differentiation problems can get a little bit messy. So this entire thing here is the answer, and there were a ton of tiny places where we could have made mistakes. The most common mistake on this type of problem is forgetting that this is really a product rule. And again, y is a function of x, so I have a function of x times a function of x. That screams product rule, so I can't forget that. And then anytime I take the derivative of something involving y, I need to make sure that I include a dy dx because of that chain rule. And the last example we'll go over involving implicit differentiation is one involving a trig function. So again, strategy stays the same. We take the derivative with respect to x of both sides first. So d dx of y equals d dx of x plus sine of y. Now on this left side, we have dy dx. And on this right side, the derivative with respect to x of just x is 1. Plus, and now here's where things get a little different, I have a trig function that is a function of y. So here I have to apply the chain rule. So I take the derivative of the outside function, leaving the inside the same. So the derivative of sine is cosine. So this is plus cosine of y. And then I have to multiply by the derivative of the inside, and the derivative of y is just dy dx. So we multiply by dy dx. And now we gather like terms on one side. So gather all the terms involving dy dx on one side of the equal sign and everything else on the other. So I'll go ahead and subtract cosine y dy dx from both sides. So I'll get dy dx minus cosine of y dy dx equals 1. Factoring out dy dx from both of these terms, I'll end up with 1 minus cosine of y equals 1. And then finally divide both sides by cosine y, or 1 minus cosine y. So finally we end up with dy dx equals 1 divided by 1 minus cosine of y.